Mathematical analysis often deals with wild, chaotic functions that oscillate unpredictably. To study them, mathematicians need a baseline, a way to strip out the chaos by applying a single, unyielding rule. The function is never allowed to reverse direction. This is the concept of monotonicity. Looking at these two graphs, we see two different ways a function can move upward. On the left, the curve is strictly increasing. It always climbs. On the right, the curve climbs, flattens out, and then climbs again. The left graph represents strict monotonicity, defined by a strict less than inequality. The right graph represents standard monotonicity. It allows for flat regions, which is why we use a less than or equal to sign. The textbook codifies these exact constraints in definition 4.28, establishing the absolute rules for monotonically increasing and decreasing functions. By strictly forbidding a function from turning around, we completely eliminate the erratic spikes and drops found in standard calculus. This creates a rigid structure that forces the function to behave predictably, even when it breaks. So, what exactly happens to these predictable functions when they do break? Let's trace an increasing function as it approaches a jump discontinuity. This diagram shows an increasing function with a clear jump. Because the curve can never decrease, all of its past values are trapped beneath its future values. It is forced to hit a hard mathematical ceiling, its supremum, which becomes the exact left-hand limit. Applying that exact logic to the right side of the break, the right-hand limit must be bounded by the floor, or infimum, of that upper section. The function's value is trapped tightly between these two limits. Because both limits are now guaranteed to exist as finite numbers, the text lays out a powerful conclusion. Monotonic functions have no discontinuities of the second kind. Let's test this. Try to picture an increasing function where the right side limit is lower than the left side limit. To connect them, the line has to drop, violating our one rule. The only type of discontinuity this function can physically experience is a clean vertical jump. If a monotonic function can only break through vertical jumps, what is the absolute maximum number of jumps it can have? Theorem 4.30 provides the boundary. This visualization highlights the empty space left behind by those jumps. Every single break creates a distinct empty vertical block right on the y-axis. Because rational numbers are dense, there is at least one rational number tucked inside every interval. No matter how microscopic the gap on the y-axis is, we can pinpoint a rational number inside it. Since our function is constantly moving upward, these vertical gaps can never overlap. This allows us to assign a completely unique rational number to every single jump on the curve. The set of all rational numbers is strictly countable. By mapping every single jump to a distinct rational number, we've proven that the total number of discontinuities must also be countable. Remark 4.31 introduces a fascinating edge case. Yes, the jumps are countable, but they can be packed so densely that a jump occurs at every single rational number along the axis. This graph builds that exact scenario. We start flat, pick a point, and step up. Then we pick another point and add a slightly smaller step. We repeat this process, cramming in smaller and smaller jumps at progressively denser intervals. As long as the total sum of all these shrinking step heights converges to a finite number, the function remains safe. It never shoots to infinity. It stays bounded, strictly increasing, and perfectly continuous at all irrational numbers. Monotonic functions lock in directional movement. That one rule stabilizes their limits, prevents erratic breaks, and restricts any discontinuities to countable, clean jumps. Even when a function fractures into a densely packed infinite series of breaks, it remains entirely mathematically predictable. If this step-by-step breakdown helped you visualize monotonicity, hit the like button, subscribe, and stick around as we continue exploring the rigorous mechanics of real analysis.